Lesson 10 demo. In this class, we learn different notation for the derivative, and we explain what the derivative represents in a variety of contexts. Number 1. This section is very notation heavy, but stick with it, and these unfamiliar symbols will become second nature for you with some effort. A brief history lesson. Calculus was invented/discovered independently by Wilhelm Gottfried Leibniz. He's on the right in this picture, and Sir Isaac Newton on the left around 1660 AD. This particular invention is incredible and sort of life-altering, but it was quite ugly at the time in terms of who should get credit for discovering this thing. You can do some reading. There's lots of information out there on the web about this ugly moment in math history, but it became very much a nationalistic, Germans supporting Leibniz and the Brits supporting Newton, and it was not pretty. Moving on to number 2, they made up different notation for the derivative. Newton wrote the derivative of x squared plus 7 as x squared plus 7 with a dot on the top. We don't use that anymore. Leibniz used the notation dy dx to represent the derivative of y with respect to x. Note the similarity between dy dx, derivative instantaneous rate of change, and m equals delta y over delta x, slope, average rate of change. That was what Leibniz was after, was capturing this idea of average rate of change, but the d instead of the Greek delta, that's also a d, representing the instantaneous rate of change, not the average rate of change. About a century later, the French mathematician Joseph Louis Lagrange invented the symbol f prime of x for the derivative. So here are 4 things that all mean the derivative: f prime of x, d dx of f of x, dy dx, and y prime. One disadvantage of Leibniz's notation, writing f prime of 3 is awkward. We write this as dy dx and then the vertical line and then x equals 3, or simply just a 3 down here. So we saw this last class. Okay, now we're going to talk about interpreting the derivative. So dy dx has units of the form y units over x units. Said another way, the derivative always has units of the form output variable units over input variable units. So number 6, for example, if g of t represents the cumulative number of gallons of water that have passed over a waterfall t seconds after midnight, then dg dt has what units? So we know that the units for the derivative are always the units for the top over the units for the bottom. The units for the top, that's for g. Units for g are cumulative number of gallons. So upstairs, the units are gallons. And then downstairs, it's the units for t. You could see a dt in the denominator. And time in this case is measured in seconds. And so the units here are gallons per second. It works out really nicely. You just put the top units on top and the bottom units on the bottom, and you've got your unit for the derivative. And I think it's helpful to write down the units when you are asked to interpret a derivative. In the context of the waterfall example, what do these 2 things represent? G of 30 equals 120. Let's start there. So that 30 is a value of t, and it means 30 seconds after midnight. And then that 120 is a value of g, which is a cumulative number of gallons of water that have passed over the waterfall. 30 seconds after midnight, 120 gallons have passed over the waterfall, and that's in total. So over the course of those 30 seconds, 120 gallons of water have passed over the waterfall. And then dg dt at t equals 30 equals 3. Let's interpret that. So the t equals 30 is still 30 seconds after midnight. So 30 seconds after midnight. And this is a derivative, so it's a rate of change. And let's think about the units here. We've already discovered that the units for dg dt are gallons per second. So the units here for this 3 are gallons per second. Something is changing at 3 gallons per second. What is changing? The number of gallons that have passed over the waterfall is changing at 3 gallons per second. Or said a little bit less awkwardly, the water is flowing over the waterfall at 3 gallons per second. So 30 seconds after midnight, water is flowing at 3 gallons per second. Now, we introduced the word flow here because we understand really well the derivative in this case, but it's okay if you are in an unfamiliar context in a problem and you don't happen to know the corresponding word like flow. You could have said something more generic in this one, like 30 seconds after midnight, the rate at which the water is passing over the waterfall is changing at 3 gallons per second. think I overused the words rate and changing there. So the rate is 3 gallons per second. The number of gallons flowing over the waterfall is increasing at 3 gallons per second, and that would be totally fine. Okay, number 7, now suppose that R is a brand new function is dg dt, where g is the waterfall function up above. What are the units of the R dt? Okay, so let's write the units here. So we need R units over T units. Now R units, let's do the bottom. T units in the bottom is dt. T units are still seconds, but R units, R is really dg dt, and we already discovered that the units for dg dt are gallons per second. So that means that the units for R are gallons per second. So upstairs is where the R units go, gallons per second. So that means that the units for dr dt are gallons per second. In a very real sense, this first derivative represents the speed of the water, right? The water is flowing at a speed of 3 gallons per second. And this is another derivative, one derivative up, and it represents the acceleration of the water. So let's see if we can write a sentence for this next one. What does this mean? The r dt at t equals 20 equals -2. So again, copying the t equals 20, we're going to start there. At t equals 20. The rate at which the water is flowing is changing by -2 gallons per second per second. The rate at which the water is flowing over the waterfall is changing by -2 gallons per second per second. Equivalently, you could say that the rate at which the water is flowing is decreasing by 2 gallons per second per second. Or you could say that the water is slowing down by 2 gallons per second every second. Lots of different ways to say that one.